Hi, my name is Mosey, and I'm doing this video as a practice exercise for my Biology 100 course. Basically, what I want to talk about today is an idea that was tripping me up, which is homologous chromosomes and ploidy. And I didn't really understand how the two work together, because my understanding is, maybe some of you have the understanding that the ploidy refers to the pairs that human chromosomes come in. So maybe chromosome looks like this. I thought this was the reason that we were diploid, is that we had a pair, right? But scratch that out, that's not the reason. So I was getting confused because we had 23 pairs. So I'm like, well, what if, why aren't we considered like 23 ploid, or, whatever the word for that would be? But we are not considered diploids. Humans are not considered diploids because we have pairs of chromosomes. We are considered diploid because even though we have 46 chromatids and 23 homologous pairs, the reason we are considered diploid is because we have two contributing parents for each homologous chromosome pair. So we have from mom and from dad. Now, when we talk about homologous chromosomes, we are talking about the set of all the inherited chromosomes from one parent. So in humans, that will be like 23. So you could imagine these are chromosomes, your dots: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And let's say this red represents a gamete cell. Well, maybe this is a female gamete cell. So one of these chromosomes, if it's a female gamete, one of these is going to be a singular X, and that's your sex chromosome. But if we were to draw the gamete from dad over here, then maybe this is the male gamete. Maybe one of these for sure is either going to be an X or a Y. Now that we understand that, we can erase all of this. Erase it better, there we go. Now that we understand that, we can talk about, for example, because we have homologous pairs of chromosomes, that means that you get a chromatid with the gene for expression A from mom, and one chromatid for the expression with the gene for expression A from dad. Autosomal, aka non-sex cells, in humans are diploid. That is, you can only make a human baby with two contributing sets of chromosomes. If a person, such as someone who is intersex, has 3 chromosomes, or has like an XXX or an XXY or just a single Y, then they will likely be sterile and not be able to have children. Now, gametes are sex cells, including eggs and sperm, which are haploid because they only have one set of chromosomes. The human haploid number is 23, and our diploid number is 46. Ploidy refers to how many complete sets, aka how many contributing parents of chromosomes you receive that carry the genes for the same expressions. Humans are diploid. This means a human baby has two sets of chromosomes, one from dad and one from mom, which join together in pairs, and therefore humans are diploid with 46 chromatids and 23 homologous pairs of chromosomes. Okay. Now that we got that out of the way, we can get to the fun stuff. I hope this video was comprehensive so far. Okay, so the activity that I've prepared that I may or may not delete if it's kind of crappy when I'm finished is this activity where I'm going to draw the sort of lineage of, oh, I forgot to add the title. We're going to be tracing the chromosomes that carry the genes for hair color, and in this activity we're going to pretend that all 7 of these hair colors are valid hair colors. The red, the pink, the orange, the blue, the green, the brown, the purple. Because that's how we roll in this house. Now, first of all, we have Gen 1, which would be, oh, I forgot to add the label too. Crap. These are the grandparents. So Gen 1 is the grandparents, and as we all know, we need 4 grandparents to make a grandbaby. Well, 4 biological grandparents, that is. So we're going to start by drawing 4 just cells that have only drawn in them the chromosomes, the homologous pair that represents hair color, and the genes that represent hair color. So now we're going to pretend like this cell right here represents a cell that is going to be broken down into gametes from grandma number 1. And I think grandma number 1 should have, and we're also going to pretend that in this exercise, all of the dominant and all of the recessive ones in the legend are equally dominant or equally recessive, to make it simple. So I'm going to decide that grandma number 1, let's say her name is Allison, for A for Allison. And she has blue hair. And the way she has blue hair is because she has that blue gene, and she also has a red gene that never got expressed. Maybe her mom or dad had a red gene that got passed on, but it never got expressed because the blue is dominant. Okay. Then we're going to have grandpa number 1, and his name is going to be Bob. B for Bob. And maybe he's going to be extremely fair. Maybe both of his parents were very fair, and they both had orange hair, and now he has orange hair. I think this guy, this girl, this grandma, her name is going to be Carolyn, and she's going to start with a C. So C for Carolyn. And I think Carolyn will have green hair. Well, 2 different expressions. I think she's going to have an interesting muddy colored hair, because she's going to have 2 dominant genes that clash with each other and make her hair a weird green-brown color. And finally, for Grandpa Don is what his name is going to be. D for Don. He again is going to have recessive hair, but this time it's going to be a mixture color between red and pink. Okay, so we know, if you've taken a biology course, you know that a regular autosomal cell, if it turns into a sex cell, it produces 4 from 1. So 4 sex cells from 1. What happens is these cells double themselves. Not in that shape, but there's 2, let's see if I can, okay, whatever. They double themselves, and then they split, and then they split again. And I'm gonna skip that step and just go straight to the gamete step. So we got 1, 2, 3, 4. And 2 of them are going to have a chromatid for blue hair, and 2 of them are going to have chromatids for red hair. Now, I might run out of space, but this is fine. So, as we know, for this guy, well, this is going to be easy. If it splits and it's all orange, and then it splits again, it's still going to be all orange. So, 1, 2, 3, 4, and this guy is 1, 2, 3, 4, like that. Not very accurate drawings, but that's fine. Then we have 1, 2, 3, 4 for Grandma Carolyn. And she's going to have 2 that have green chromatids and 2 gametes that have brown chromatids. And then Grandpa Don is going to have 1, 2, 3, 4 gametes. And what did I say? Pink and red. So 2 are going to be pink, and that's not red. I'm tired. And 2 are going to be red. I have midterms next week, so that should be fun. I didn't draw this step all the way through because you guys understand if you've taken a basic biology course, Bio 20 or Bio 30. So now we have our gametes, and now we get to choose a random selection, which I don't even know. I haven't planned out. Let's just say that Mom, let's say this is a female child, so this is Mom, and her name is Melissa. And let's say this dude over here, his dad, and his name is going to be Tom. Melissa and Tom. And now what we have to choose from here is all orange, so she's definitely going to have that recessive gene because her dad has orange hair. But she might get a recessive gene as well from her mom, from Allison, or a dominant gene. But let's just say that she got 2 recessive genes, one that is red and one that is orange. Okay, now for Tom, we can see that there's 2 recessive genes here and 2 dominant genes there. So why don't we go ahead and say that he inherited a green from Carolyn, green hair, and a pink hair gene from Don, his dad. Now, let's draw out the gametes, and then we're going to draw out the potential babies. So if Melissa and Tom have a baby, what is their baby going to look like? Or what's the colors their hair going to be? So draw out the gametes. I'm not going to do that step again. 1, 2, 3, 4. 1, 2, 3, 4. Okay. And I need 2 oranges for the chromatids and the gametes from Mom. Chromatids and the gametes for Dad. And then we're going to draw out the chromatids for Dad. And he got a red one or a pink one? I think that one's pink. It's hard to see in this lighting. Okay, so those are their gametes. Now, so let's say he got a green from Dad. The baby, whoever the baby is, got a green from Dad and an orange from Dad. Or maybe an orange and a pink, so it's recessive. Or maybe a red and a pink. Or a red and a green. Now, let's determine these babies' hair colors. So, since we know green is dominant and orange is recessive, if this option number 1, 2, 3, 4, if we choose option number 1, or it happens, the gene pool gives you option number 1, this child's hair is going to be green. And since orange and pink are equally recessive, it's going to be like this mix of orange and pink. Now in this case, we got the red and the pink. Again, that is going to be a recessive hair color. It's just going to be pink and red instead of orange and red. But that is two recessives together makes a recessive, right? And then in this case, because we know green is dominant over red, this child's hair, this child's hair would be green. Okay, so whoever you are on the internet, I want to say good luck with your future studies. Goodbye.